Good afternoon, everybody. Today, I'm going to be talking and introducing the topic of how we measure dynamic soil properties. We've talked a lot about how waves propagate through different materials in the recent weeks, and a little bit about vibratory motion, and just learning about waves in general. We've talked about the equation of motion, and I introduced to you the concept of damping. And now, if we're going to actually compute how waves travel through different property, or how waves travel through different types of soils, we need to be able to measure and come up with estimates of the soil's what we call dynamic properties. And what do we mean by dynamic properties? Well, we may mean the velocities of the waves, so the P and the S wave velocities in the material. These are the propagation velocities, not the particle velocities, but the P and S wave propagation velocities. The damping characteristics of the soil, what percent damping ratio are we talking about, as well as the moduli of the soil, so the shear and the constrained moduli. Those are the things that we're after when we talk about dynamic soil properties. So if we want to measure dynamic soil properties from a particular soil, there's a couple different ways we can do it. These ways have been developed over the last few decades, and each of them have their advantages and their disadvantages. And now we can take all of these different methods and we can sum them up and classify them according to two generalized groups. There are field methods. These are in-situ methods where we take equipment out to the field and we try to measure the dynamic properties of the soil as it is in the ground. And these could be subdivided into different classes. We have low strain tests where we're inducing shear strains in the soil that are less than 0.001%, so really small strains. Or we can induce high strain tests, which are strains that are larger than that percentage. The second general group is what we call laboratory methods. And again, we can have low strain laboratory methods or high strain laboratory methods. We're going to talk about all of these today and introduce you to some of these approaches that geophysical and geotechnical experts use to characterize the properties of soil. So let's look at the field methods first. When we talk about field methods to characterize soil dynamic properties, really what we're talking about is a field called geophysics. And this is a big deal. There are a lot of experts in this field that are specialized, and we're going to kind of wet your whistle a little bit with the material that we'll present here, but by no means will learning this stuff make you an expert. This is some pretty sophisticated and advanced stuff, and there are several experts that dedicate their entire education and career to just this topic. And so, but hopefully what you learn in this lecture will enable you to communicate with these experts and to have a better understanding and appreciation for the types of things that they do. So when we talk about low strain field testing or low strain geophysical testing, typically what we're going to do is we're going to arrange a series of geophone receivers across the site. So a geophone is a velocirometer. I know that sounds like a dinosaur, but it's like, think of an accelerometer, but it measures velocity. And so we're going to lay these geophones across the site, and then we're going to introduce some sort of seismic source into the soil. There's different ways to introduce this seismic source. We can do like a vertical hammer blow, where we just go out and we hit the ground surface with a hammer, and that's going to induce S waves, it's going to induce P waves, and we're also going to get Rayleigh waves, and all of these waves are going to generate and propagate out through the soil. And so our geophones are going to pick up all of the arrivals of these various waves. Another thing that we could do is use an explosive. So this sounds fun. We can go ahead and put the explosive in the ground, and the explosive sends out a giant pulse in all directions, and that pulse is comprised only of P waves. And then we could also do like a horizontal hammer blow. And so, you know, I've always wondered how this happened. How do you do a horizontal blow on the ground surface? That, you know, I understand the vertical hammer blow, but how do you do a horizontal hammer blow? Well, I learned how to do it. I saw the geophysicists, they put a board on the ground and they pinned it to the ground surface. But you ask yourself, how in the world do they pin it? Well, they drove their truck up on top of the board so that it stuck, you know, there was a lot of vertical force pushing it down on the ground, and then they hit it on the side with the hammer. And that induces just S waves. No P waves, no Rayleigh waves, but just S waves into the ground. So the most basic geophysical test that we can perform is called a seismic reflection test. The seismic reflection test is going to measure the wave propagation velocity and the thickness of our superficial layers. So this test is going to assume that we have a two-layer soil system and that the second layer is going to have a higher propagation velocity than the first layer, that it's going to be more dense and it's going to be more stiff. So what this approach assumes then is that we're going to have our source. The source is going to put out its waves. The wave is going to travel down, and when it hits this denser, stiffer layer, there's going to be a reflection. And the reflection wave is going to bounce back and travel up, and we're going to have a receiver, and the receiver will eventually pick up the reflection of the wave. But in addition, we're also going to have a direct wave that's going to be sent out from our source, and the receiver is going to pick that wave up as well. So how the seismic reflection test works is we're interested in the time for the reflection wave, and that's this T sub r. And we can compute T sub r as, using this equation where h is the thickness of our upper soil layer, x is the distance between our seismic source and our receiver, and v is the propagation velocity of our soil layer. So what we're going to do is we're going to compute v from the direct wave. So we know the distance x, and we just have to look at our receiver and look when the direct wave arrives at the receiver. Once we have that, we have time. X divided by time gives us velocity. And then once we have velocity, we can, again, plug in our x. We know the time because we're measuring it, so all we need to do is compute our thickness of our soil layer. That's really what we're after, is the thickness of that upper layer. And, you know, we can be either looking at the P waves or the S wave velocities. It completely just depends on what type of seismic source you're looking at. Okay, another type of in situ geophysical test, low strain test that's popular is called a seismic refraction test. Now this is more complex than the reflection test. The reflection test is going to assume nice horizontal layers and just a nice two-layer system. If I have seismic refraction, I'm not going to have just one receiver, but I'm going to have multiple receivers laid out in a line along the ground. And then I'm going to have my explosive charge, and what's going to happen is all of these receivers are going to be picking up the different travel times of the first arrival wave. So you can see on this plot up here I have arrival time and I have distance from the seismic source. So you can see that the further away we are from the seismic source, the longer the arrival time is going to be. And really what we're trying to measure with this type of test is the wave velocity in both the upper layer and the lower layer. We're also going to measure the thickness of the upper layer, and we're going to measure the profile of the lower layer. What I mean by that is we're going to measure the profile of the boundary between the two layers here. And that's pretty neat because it doesn't need to be a flat horizontal line. As you're going to see in your homework assignment, it can be sloping, it can be doing all sorts of weird shapes, and we're still going to be able to pick it up. So what we're going to do is we're going to take this plot of our arrival times versus our distance, and we're going to draw some straight lines. The first straight line here, as we draw that line, the slope of that line is going to be essentially the inverse of the propagation velocity for layer number 1. And then if I take the next slope on my plot and I draw a tangent line through those points, the slope of that line is inversely proportional to the propagation velocity of the second layer and the third layer, and however many layers I want. This method is not confined to just 2 layers. We can have multiple layers if we wanted to. We're going to make the assumption then that we are getting stiffer and denser with depth again. In other words, the velocity for layer 3 is going to be greater than the velocity for layer 2. It's going to be greater than the velocity for layer 1. So in this test, we are only concerned with the critical angle of incidence. Now, what is the critical angle of incidence? You'll recall that the seismic source is sending out waves in all directions, right? And when these waves come down, they're going to hit the boundary and there's going to be a reflection. And, you know, but the critical angle is the angle at which, when this wave comes down, essentially the transmitted wave, instead of transmitting at different angles, as you know some of these waves might do, the transmitted wave at the critical angle transmits right along the boundary. So it just follows that boundary all the way. And this wave is a special wave because when the wave's traveling right along the boundary, it is constantly sending off reflected waves all the way back up to the surface, just nonstop. And all of those reflected waves are going to come back up at the surface at the same angle, at the critical angle. And those are the waves that our receivers are trying to pick up. So the idea with this test is that the transmitted waves in these lower, denser layers are going to travel faster than the waves in the upper layers. And eventually, the incident waves in these lower layers are going to get well ahead of the direct waves because they're faster. At which point, once these incident waves in the denser material get well ahead, those head waves from the incident wave are going to arrive before the direct waves do. You know, a good example of this would be, let's say I live in I live in Springville, Utah. So we can say, all right, let's imagine I want to get to Orem. Okay. Well, if I want to get to Orem, Utah, if I just take the quickest distance geographically from Springville to Orem, I would stay on the surface streets going through all the communities, and I would eventually just make my way to Orem. But you know that the speed limit on those surface streets is much slower than if I go out of my way a little bit, get on the freeway where I'm traveling at a much faster velocity, And at that point, eventually I'm going to get to Orem faster because I'm traveling at a higher velocity than if I drive on the surface streets. I mean, that's all that this stuff is telling us. It's like these waves, these incident waves get down, and as they come up, all the head waves are coming off the incident wave. Think of those head waves as traveling on the freeway, okay? And these direct waves are traveling on the surface streets. So, because we're interested then in these head waves that are coming up, and they're coming up at the critical angle, incident angle, we can go ahead and perform a little bit of math. Now, here's our seismic source, and we have one of our receivers. Now, the distance to that particular receiver we call x sub n. We know that the soil has some thickness, layer H, but we don't know what it is. And then we know that there's some critical angle. We may not know what that is yet either, but we're going to try to solve for these things. So we can compute an equation to give us the thickness of the soil layer. And that equation is going to be given right here, where, again, we have this, let's see, we have all the values here, where v sub 2 is going to be equal to the propagation velocity in the lower layer, v sub 1 is the propagation velocity in the upper layer. So then, if the ground is sloped, which it commonly is, it's going to make things a little bit more complicated. And so usually we have to assume that the ground is sloped. And if that's the case, we have to run our seismic sources both ways. Meaning, if this is my ground surface, and this is what my soil profile looks like below, I'm going to have my geophone set out all along the ground surface. And I'm going to do my seismic source in this way, which will send the waves down this way with all the head waves coming off. And we're going to read everything going that way. But then, whoops, let's see. But then we're also going to do the seismic source on this end with the wave going the other direction. And that wave is going to send off all its head waves, and we're going to read those coming the other way. So that's what we need to do if we suspect there's going to be sloped ground. And if that's the case, then on our arrival time versus distance plot, we're actually going to have two sets of lines. One set of line is going to give us our velocity slopes going one way, and the other line is going to give us the velocity slopes going the other way. If the ground wasn't sloped, these two sets of lines would look like mirror images of one another. But you can see that that line is shorter than that line, which suggests that, yeah, we've got sloped ground going on. Okay, so if that's the case, then we need to solve a couple of parameters, okay? The parameter alpha we can solve using this equation right here. And then once we have alpha, we can solve the critical angle or critical incident angle using this equation right here. Now, the D implies in the down direction, and U implies in the up direction. You decide what you want to call down or up, but this curve in this plot you can see is called down, and this curve in this plot is what the geophysicist is referring to as the up direction. So you just got to be consistent however you're defining it, okay? But then once we get the critical incident angle, we can solve for the true propagation velocity in the lower layer by using this equation right here. And that'll give us some pretty useful information. By the way, this alpha angle here, that is equal to the boundary inclination. So that's the angle of the boundary between layer 1 and layer 2. So then what we can do is that we can solve the depth from the ground surface to the top of layer 2. So the thickness, I guess, of layer 1 at any location or any distance here. So given this distance right here, we can say, all right, I know the time in what I say time d1, this is from my upper curve, or from my first curve, and time d2, that's from my second curve. So I mean, you could have u's there and d's if you wanted to, but you know, that's fine. So d1 is from my first set of curves, d2 is from my second set of curves, and t sub t, that's just going to be the termination time for both waves. Both waves, because we're dealing with the same material, should have the same arrival time at the last geophone. And we already solved for the critical angle, and we can get the average shear wave velocity in the upper layer. And so what that's going to give us is at this particular location on my line, that's going to give me the depth or the thickness of the upper layer and the depth to the boundary for the second layer. So, you know, if I moved over to this point right here, I would pick that little dot that I'm drawing as my TD2. This little dot that I'm drawing is TD1, and I would solve for this thickness right here. So by the time you're done going all the way over, really what you need to understand with regards, with regards to Z sub D is that this really is the depth to the critical wave. So again, this is the wave that's coming down, hitting the second boundary and just traveling along the boundary, and then popping up as a head wave at the incident angle just in time to make it to our last receiver. So this Z sub D is just the depth of following this wave. So when you plot your plots, what you're going to show here is like distance, and you're going to plot Z sub D. What you're going to see is something that's going to look like, you know, this. Okay, the ground surface really doesn't look like this on the ends of your geophone line. You got to remember that those sloping down and sloping up, think of those as the wave paths back or from the source down to the boundary, and then from the boundary back up to your last receiver. But this stuff right here in the middle, that does represent the boundary between layer 1 and layer 2. So it's almost like we're doing an think of it as an ultrasound of the ground beneath our feet. And what's neat is we're doing this without putting a single boring or hole in the ground. So let's talk a little bit and differentiate between seismic reflection and seismic refraction. What are they good for? Well, they're definitely good for dealing with layers that consistently become denser with depth. So if we have a soil layer system where the soil layers are getting denser and denser and denser as we go down, these methods are going to be great. They're great if you're dealing with nice terrain, and they're really effective. And in my own personal practice, they were always the most useful when I was just trying to map the boundary between two high contrast, high impedance soils, where the lower soil or rock was a lot more dense than the upper soil. So maybe like the boundary between soil and bedrock. So you can imagine like gold miners, for instance, use these methods a lot so they can locate the bedrock beneath their feet, and they know how deep they need to go to bedrock to find the best gold nuggets. These methods are bad for other situations. For instance, what if my soil doesn't become consistently deeper with depth? What if I have intermittent soft soil zones? If that's the case, then the assumptions we made in deriving our equations are false, and we're going to get some wacky predictions. And these methods can also be really bad if I'm working in extremely difficult or very hilly terrain where the subsurface is doing some weird shapes, because we can get some weird reflections and transmissions where our assumption of the incident angle doesn't really hold true. Another popular in-situ geophysical method is what we call surface wave methods. And these have gotten pretty popular in about the last 25 years or so. It's much, much more sophisticated than the methods that we just learned of seismic reflection and seismic refraction. And it's more complex because it involves the production and the measurement of Rayleigh waves. So we're looking at surface waves, specifically Rayleigh waves. And what we're going to do is we're going to break down the pattern of the Rayleigh waves. We're going to do a spectral analysis using the Fourier spectra recorded from each geophone. And we're going to go ahead and interpret these Fourier spectra, perform some inversions, and then perform some interpretations of the dynamic properties of the soil layering beneath the site. So we're going to come up with thickness, dynamic properties. Those are the main things we're going to try to get from these methods. Now, you got to understand, these methods, they are reliable, but the reliability of them is 100% dependent upon the qualifications and the experience of the person performing the analysis. They're very subjective, and so you always want to be careful who you get to perform the analysis. You want that person to be a seasoned expert, preferably someone who's had lots of years, preferably graduate school training, doing these types of studies. So when we talk about surface wave methods, there are generally two well-accepted methods in practice. There's the spectral analysis of surface wave methods. This is the SASW. And then we have multi-channel analysis of surface waves method, or MASW. So despite the fact that these methods are pretty subjective, they are already very popular, and they're getting more popular for a few reasons. I mean, first of all, we can deal with complex soil stratigraphy. We can deal with the fact that there might be hilly terrain, that the subsurface might be doing lots of weird stuff. We can handle that with these methods. We can also detect and what I call see through soft soil layers. So we don't need the assumption, or we don't need to use the assumption that the soil is getting denser with depth. We can do just fine if there's a soft soil layer down there. And in fact, these methods are used from time to time to look for soft soil pockets or zones or peat deposits to try to find them without having to turn the ground into Swiss cheese by putting a whole bunch of borings down. And these methods are becoming increasingly more affordable to perform. When I left consulting, 5-6 years ago, the price to perform one of these tests on your site was about $5,000, which in the consulting world is next to nothing. I think licensed geophysicists would probably charge more, but you can usually find some academic or a professor and his or her student, and they're going to give you a lower rate, closer to $5,000 or $6,000, $7,000 maybe. If we compare these two different methods, MASW and SASW, they each have their advantages and disadvantages. Let's talk about MASW first. It tends to work better in noisy environments. So if you're in urban environments or the city where you have lots of traffic, maybe urban construction going on, MASW is going to be a little bit easier to interpret. It does have higher resolution at shallower depths than SASW does, but it generally is more difficult to perform and analyze than SASW testing. Now, SASW testing, on the other hand, it does not work very well in noisy environments, but if you have an environment where you can perform reliable readings, you can get really good resolution even at great depths, like tens, potentially even hundreds of meters down, depending on the spacing of your geophones. And it's also a lot less complicated than MASW, in my opinion. Okay, we're still dealing, folks, with low strain field methods. So here's some other methods that are commonly used in practice today. We have what are called borehole methods. So if we have borehole methods, we're going to drill a hole in the ground, and we're going to start playing games essentially with sources and receivers. We can use the source and the receiver in a whole bunch of different ways to try to measure what the wave propagation velocity is in the soil, from which we can also get the shear modulus or constrained modulus, and whatever, and the damping as well. So the first test is what we call the Uphole test. So this is where we're going to put our source down in the ground, and the source usually has these little pneumatic clamps that when you trigger them, they shoot out and press themselves really tightly against the boring wall. So then you have a rod that comes all the way up, and you start banging the rod with your hammer. And what that's going to do is it's going to send these waves out in all directions from the source where it's touching your wall. And you're going to have a receiver some known distance from your borehole, and you're going to know the depth that you're down, from which you can compute the distance or the length from your borehole to your receiver, and so we can compute directly the propagation velocities that way. Another way, a different iteration of this, is what we call downhole. So in this particular case, we put the receiver down the borehole where it lodges up against the sides of the borehole wall, and then we have our source up on the ground. We still have the same distances, so the only difference is now our wave is going towards the borehole instead of away from the borehole. There's instances where it's advantageous to drill two boreholes and put a receiver in one, the seismic source in the other, and what we're doing is we're measuring the direct propagation velocity between these two boreholes, and we call this a crosshole test. Crosshole test has lots of useful applications, not just in soil, but we've seen instances where if I'm putting down like a drilled shaft, if this is the ground surface, and I'm building this big drilled shaft in the ground, and I want to know that how competent and the integrity of this drilled shaft at the various depths within it. Oftentimes, when we construct these drilled shafts, we'll put these PVC pipes all the way down. And these pipes would extend all the way down to the bottom of the shaft, of course. So anyway, I mean, you get the idea. So this shaft is built with concrete. The concrete cures and everything's fine. And what we do then is we'll stick our receiver down there. We'll stick our seismic source down there. And we'll go ahead and do crosshole testing all the way down the drilled shaft. And then we'll stick the source and the receiver in other holes. And we'll just work our way around the drilled shaft and recording then the propagation velocity all the way down the drilled shaft to its very bottom. And that propagation velocity, of course, correlates directly with the integrity and the quality of the drilled shaft foundation. And so if there's any holes or places where the concrete never got in, we're going to pick that up with that crosshole test. Another method that is really kind of interesting is an in-situ method where we do what's called a seismic CPT. So most of you have learned what a cone penetration test is, and we use it to get a lot of useful geotechnical properties of the soil. One of the some clever researchers decided it would be cool to put a geophone in a CPT. And so now as the CPT is being pushed down through the ground, at whatever depth the CPT is at, we can stop the test and pound a seismic source on the ground. So we know the depth, we know the distance from, again, the cone to our seismic source. So from that we can compute the direct distance from our receiver to the source, and we can measure the arrivals of the waves that we induce and then get the propagation velocity of whatever soil layer that we're in. So advantages and disadvantages of these borehole methods. In terms of advantages, we usually get really good data. It's very reliable. We can see it. Whenever I see borehole geophysical data, it's usually worth its weight in gold. We can also get soil samples in the process of drilling our borings. Or performing CPTs, we can at least get in situ soil data and more properties just about the geotechnical properties of the soil. And so that's usually advantageous. And there's very little subjectivity in the results. I mean, what we measure is what it is. We don't have to make any guesses or assumptions. It is what it is. So disadvantages, these methods are much more expensive than other geophysical methods or where that don't involve putting a boring into the ground. The measurements are also limited by the borehole depth or the CPT depth, and so and that could also have limitations due to cost. So most of these holes are typically shallow, though at times I have seen some very deep boreholes that get down into rock and start measuring the velocities of the rock, but man, those things are expensive. And then we also have to deal with the practicality and the environmental issues. When we drill boreholes, it usually makes a big mess, and depending on where we are, the laws that govern how we clean up boreholes and deal with boreholes are usually pretty challenging, particularly in California. And these methods can also be pretty time-consuming as well, which also relates back to cost. Okay, so that wraps up our in-situ low-strain testing. Let's talk about in-situ high-strain methods. So again, these are methods where we're really going to induce some deformations into the soil, and then we're going to correlate them back to shear wave velocity. Something that I need to warn you about when we talk about high strain. You've got to be aware of what's going on. When we talk about dynamic properties of soil, folks, we're talking about shear or constrained modulus, we're talking about shear modulus, we're talking about damping, we're talking about all of these properties that relate to the elastic nature of the soil. But when we do high strain tests, we're not deforming the soil elastically. We're inducing large strains, plastic strains in the soil. So we're not directly measuring these dynamic properties in any way. We're correlating them. And so you have to be careful and understand that with high strain field methods, it's all based on correlation. We're not measuring any actual dynamic properties. So there's correlations with the standard penetration test. There's correlations with the cone penetration test. But like I said, all these correlations have lots of scatter associated with them. And so anytime you deal with scatter, you have to account for the fact that your best estimate line, whatever that is, may not actually be what the true value is. Now, field methods are nice because they tell you a little bit about the properties of the soil in its in-situ state. And I love field methods. They're usually cheaper, and I trust the results a lot more because we're leaving the soil in its state as it is in the ground. But it is pretty difficult to measure the damping properties of the soil. Really, in my understanding, which is limited, really the only way we can get damping is through the surface wave geophysical methods. And so one of the best ways that we can have to measure the damping properties of the soil is to get the soil into the laboratory where we can do some more controlled testing of it. And so we're going to switch gears and talk about laboratory test methods now. So anytime, though, we talk about bringing soil samples back to the lab, especially to measure low-strain dynamic soil properties, the biggest challenge you're always going to deal with is how in the world do I get an undisturbed sample of soil to the lab? Getting the soil out of the ground and transporting it is always going to disturb the soil to some extent. So the name of the game is how do I minimize the disturbance to the soil? So everything I'm going to talk about now assumes that we got a relatively undisturbed soil sample back to the lab. And so I really don't want to undersell, though, the importance of getting high quality, minimal disturbance soil samples. It's a challenge, and you have to rely on experts who are very good at site characterization and sample retrieval to do this. Okay, but let's say we've got our soil samples back at the lab. The first test I want to talk about is what's called a Bender element test. Bender elements are essentially just little electrodes at the top of the soil sample and at the bottom of the soil sample. We can put them inside of triaxial tests. We can put them inside of direct shear tests. We can put them inside of just plain containers. But all that matters is that we have an electrode on the bottom and an electrode on the top. And what we're going to do is we're going to run an electric current through the soil, and through which we're going to apply a very small but controlled and measured shear pulse into the soil. Well, before I go on to the next test, let's talk a little bit more about this. So that shear pulse, because it's very, very small, we can measure the strains with great precision. The challenge, of course, is inducing very small strains in the lab. That's difficult to do mechanistically, but using these little teeny electric currents, we can get some very, very small strains induced into the soil. The next test is what's called a resonant column test. So the resonant column test looks kind of like a triax test, but it's a lot more sophisticated. What it has here on its cap, if I turn that cap and flip it up and look at it from the top down, it's going to look like this. And the cap has a whole bunch of these magnetic coils along the outside. And these magnetic coils have the ability to attract or repulse one another. And so what they can do is they can basically cause a torsion to be applied to the soil. And it can be extremely small, a very, very small torsion, or a very, a larger torsion if you want. And then we can apply a normal confinement stress to the soil as well, to try to imitate what the soil is feeling in the ground. So the resonant column is trying to apply really small torsional shear strains to our soil. And then what it does is it can apply the torsional shear strains in a cyclic manner, meaning that if this is shear strain and that's time, it's going to apply like a harmonic wave of shear strain to the soil. And then we can adjust the frequency of that wave as well as the amplitude if we wanted to. But the point is, if I just adjust the frequency and leave the amplitude constant and we measure the accelerometer output, what we're going to find, and the accelerometer, of course, being the accelerometer that's mounted on the lid of the resonant column test, what we're going to find is that certain frequencies of our applied waves, or a certain frequency, is really going to get that soil humming. And that, of course, would be the soil's resonant frequency, and that's where resonance is occurring in the soil. And from that, then we can compute our dynamic soil properties as well as our damping properties. Okay, now we're going to talk about high-strain laboratory methods. Now, high-strain tests can give us some pretty useful results, and they can tell us the dynamic properties of the soils after large strains have been induced. Now, this information is useful if we combine it with low-strain tests because it gives us a more complete picture, low-strain and high-strain deformations and what the properties of the soil are corresponding to those strains. But again, getting an undisturbed representative soil sample is the largest challenge associated with this laboratory method as well. So a couple of the high-strain laboratory methods. You've learned a little bit about the triaxial test in my undergraduate elementary soil mechanics class. Now, take that same triaxial test and just imagine now this little box being on the ram. This little box is a load cell that has the ability to load cyclically. It can load up, it can load down, load up, load down, and so what we're doing is applying a cyclic vertical stress. And it's compressional in nature. But when it loads off, it induces tension in the soil. And so we get compression, tension, and it's trying then to mimic cyclic loading in the soil. Some advantages and disadvantages of this test. In terms of advantages, we can use the triaxial cell to model both isotropic soil conditions. You recall isotropic is where, say, that the horizontal properties of stresses is equal to the vertical horizontal properties. So in other words, if I say, you recall that K, when we talk about lateral earth pressures, is the ratio of the horizontal stress to the vertical stress. If the soil is isotropic, the horizontal stress is going to equal the vertical stress. And that would be for the case where we're only relying on the cell pressure itself to confine the soil. Anisotropic would be where the ram is going to be used to provide some anisotropy to the soil in addition to the shearing. Another advantage is that we can apply the stresses to our soil uniformly and that we're not concentrating the stresses on any particular region of our soil sample. But disadvantages, it's really hard to model shear waves when we're loading the soil in compression and tension vertically. So what we really have is the wrong loading mechanism. The up and down motion of the cyclic triaxial test doesn't really represent the side-to-side shear motion that earthquakes induce on the soil. And it's difficult to measure strains that are smaller than about 0.01%. We're going to have to rely on like resonant column or bender element tests to do that. So, but what can we do if we have cyclic triaxial tests? Well, we can measure, say, the damping ratio. So here's a great example. I encourage you guys to, pause and read through this example and look at. Really what we're doing is we're performing one cyclic cycle of a cyclic triax test, and we're going to measure the damping ratio of the soil after this one cycle in the test. So of course the damping ratio is going to change with each cycle as the soil degrades and gets more and more damaged. But so go ahead and pause the presentation and just take some time and look through this example and spend the time you need to understand what's going on. Okay. Another test that is less commonly used in practice and more commonly used in universities and academic research is called the cyclic direct simple shear test. Now, this is like a direct shear test, but it's superior because what we have is, let's see if I can even draw this. Imagine if I have this base pedestal, and on this base, I start stacking some steel rings. So it's almost going to look like a slinky, right? And then inside of those rings, I put my soil sample. And after I put my soil sample, I put the cap on it. And so, the soil is contained inside that slinky thing. And then say I start applying a shear, I can apply a normal stress to it like we do in a direct shear test, but then I can apply a shear stress to it. And because these rings can slip past one another, what ends up happening, the rings provide confinement, but they allow the soil to deform in any way that it wants to. Contrast this with a direct shear test where I have a box where the soil's in, and when I pull one box relative to the other box, it forces the soil to have a shear plane right between the two boxes. And that's kind of a no-no because the soil doesn't want to shear that way. Because I have these flexible rings, the soil in a direct simple shear test can deform and shear any way that it wants to. So the only difference now between the direct simple shear and the cyclic direct simple shear is that my shear box here can shear back and forth in a cyclic manner. And so that's what we've got. This is just a cross-section of that test. So advantages and disadvantages of this cyclic direct simple shear test. That cyclic motion and the ability for the soil to deform how it wants to while still being confined is a much better simulation of what the soil is actually feeling in the ground in a real earthquake. We get the side-to-side shear stresses, not the up and down compressional and tensional stresses. This method has been shown to produce some really useful and valuable liquefaction results in the laboratory. Disadvantages, however, is that there's no way to measure the complementary shear stresses on the sides of the soil, and because the rings deform and allow the soil to move however it wants, we really don't develop many complementary shear stresses on the side of the soil. And there's usually limitations on the stress states. And when I say stress states, again, I'm talking about anisotropic versus isotropic consolidation of the soil. This test is very expensive to perform. It's much more expensive than a triaxial test, and it's hard to find an apparatus. Like I said, the only apparatuses that I'm aware of are at universities, and they're usually tied up pretty heavily on testing. And so you kind of have to get in line and wait your turn if you ever want to use these devices. Okay, I think this is the last device we're going to talk about in terms of laboratory methods for high strain. We have a cyclic torsional shear device. So in this device, what's going on is we load the soil into a tube and we put a lid on the sample, and then that lid turns and it can induce shear down through our soil, but it's torsional shear, and it can spin and turn as much as it wants and induce as much torsional shear as we would like in the soil. So advantages, we can get isotropic and isotropic conditions in this test, and because we can just spin that lid as much as we want, we can essentially achieve unlimited strain until the soil just shears. But we do know from this test that we get uneven strain from the middle of the soil sample out to the outer edge of the sample, unless we use really specialized, expensive equipment. The preparation of your sample and getting it loaded into this device can be very difficult. It's very expensive to perform because, of course, finding someone with an apparatus is next to impossible. They have one of these testing apparatuses at my alma mater up at the University of Washington. So folks, that's it for that Dynamic Soil Properties 1 lecture. Stay tuned for the Dynamic Soil Properties 2 lecture, where we're going to show you a little bit more about what we're going to do with the soil dynamic properties once we have them. Thank you for your attention and have a great day.